Welcome to our exploration of major geological processes associated with plate tectonics. Earth is a dynamic planet, constantly in motion due to internal and external forces. These forces shape the land, influence climate, and impact all living things, especially humans. From earthquakes and volcanoes to tsunamis and fault ruptures, the effects are felt worldwide. Understanding these processes is crucial for predicting natural events and minimizing their impact. This journey will deepen your knowledge of how Earth's movements create continents, mountains, and valleys, and how these changes affect our lives. Let's begin by setting the stage for the fascinating world of plate tectonics. Understanding plate tectonics is not just about science, it's about safety and survival. Knowledge of Earth's movement helps us predict earthquakes and volcanic eruptions, allowing communities to prepare and reduce damage. It also explains the formation of continents and landforms, giving us insight into our planet's history. By studying these processes, we can locate valuable resources and anticipate environmental changes. This unit builds on previous lessons about Ethiopia's geological history and the formation of continents, offering a comprehensive look at the forces that shape our world. Continental drift theory revolutionized our understanding of Earth's continents. It proposes that continents have moved over geological time, drifting across the ocean bed. This theory suggests that all present continents originated from a single supercontinent called Pangaea, which existed around 350 million years ago. During the Triassic period, Pangaea began to break apart, forming two major landmasses, Laurasia in the north and Gondwanaland in the south. Over millions of years, these landmasses further subdivided into the continents we know today. The concept of continental drift laid the foundation for modern plate tectonics. After Pangaea split, two distinct landmasses emerged, Laurasia and Gondwanaland. Laurasia comprised the northern continents, while Gondwanaland included the southern continents. These supercontinents gradually broke apart, giving rise to the continents we recognize today. This process, known as continental drift, took millions of years and was driven by powerful geological forces. The breakup of Pangaea explains the similarities in rock types, fossils, and mountain ranges found on different continents. Understanding the origins of Laurasia and Gondwanaland helps us trace the history of Earth's surface. Alfred Wegener, a German meteorologist, proposed the continental drift theory in 1912. He introduced the concept of Pangaea to explain ancient climate similarities, fossil evidence, and rock structures between Africa and South America. Key evidence includes the remarkable fit of coastlines, similar rock types and ages across continents, and mountain belts that extend from one continent to another. Fossils of organisms like Mesosaurus found on both sides of the Atlantic further support the theory. Paleoclimatic data also reveal similarities in climate across continents, reinforcing the idea that they were once joined. Despite compelling evidence, Alfred Wegener's continental drift theory faced skepticism from the scientific community. One major reason was the lack of a clear mechanism explaining how continents could move. At the time, geologists believed continents were fixed and could not drift across the ocean floor. Wegener's ideas challenged established views, and it took decades for the theory to gain acceptance. Eventually, advances in technology and new discoveries provided the missing links, paving the way for the plate tectonics theory. Building on continental drift, plate tectonics theory emerged in the late 1960s. It describes how Earth's lithosphere, the uppermost mantle and crust, is broken into large plates that slide over the asthenosphere. These plates move slowly, changing size and shape over time. Plate tectonics explains the movement and deformation of Earth's outer layers, revolutionizing our understanding of geological events. The theory provides a framework for predicting earthquakes, volcanoes, and mountain formation, and explains the distribution of fossils and rock ages. Earth's lithosphere is divided into about a dozen major plates plus several smaller ones. These plates can be made up of continental rocks, oceanic rocks, or a combination of both. They move at rates of a few centimeters per year, driven by forces within the Earth. The boundaries between plates are sites of intense geological activity, including earthquakes, volcanoes, and mountain building. Identifying the major plates and their boundaries is essential for understanding global geological processes. Interaction of tectonic plates occurs at their boundaries, which can be classified as convergent, divergent, or transform. The type of boundary depends on whether the crust is oceanic or continental. Continental crust is less dense than oceanic crust, influencing how plates interact. At boundaries, plates may converge, diverge, or slide past each other, each process leading to distinct geological phenomena. Understanding plate boundaries is key to predicting and explaining Earth's dynamic surface. Convergent boundaries occur where two plates move toward each other. The denser plate is forced under the less dense one, a process called subduction. This leads to the destruction of crust and the formation of features like volcanic arcs and mountain ranges. When oceanic plates converge, volcanic islands such as the Mariana Islands are formed. Continental crust convergence can deform the crust, lifting one plate over the other. These boundaries are sites of intense geological activity and dramatic landform creation. Divergent boundaries are where plates move away from each other, typically at oceanic ridges. Rising magma from the asthenosphere creates new seafloor, pushing plates apart. Undersea volcanoes and crust expansion produce long ridges with central rifts. This process, known as seafloor spreading, is common at oceanic ridges like the mid-Atlantic. Divergence can also occur on continents, forming rift valleys such as the East African Rift Valley. Shallow earthquakes often accompany these movements. Transform fault boundaries occur where plates slide past each other laterally along fractures in the crust. These faults are common on the seafloor along oceanic ridges, but also appear on continents such as the San Andreas Fault in California. The plates stick and occasionally slip, producing earthquakes. Unlike convergent or divergent boundaries, transform faults neither create nor destroy crust. They are significant sources of seismic activity and can cause major earthquakes. Late motion is driven by forces within the Earth, including convection currents in the mantle, gravity, and the pull of subducting plates. These forces cause plates to move, collide, and separate, shaping Earth's surface over millions of years. Retarding forces such as friction and resistance at plate boundaries can slow down or alter plate movement. Understanding these forces is essential for predicting geological events and explaining the formation of landform. Movement of plates is closely related to their boundaries. At convergent boundaries, plates collide and crust is destroyed. At divergent boundaries, plates separate and new crust is created. Transform boundaries involve plates sliding past each other, causing earthquakes. These movements explain the distribution of mountains, volcanoes, and earthquakes around the world. By studying plate boundaries, geologists can predict where geological events are likely to occur. Plate movements have profound effects on human lives. Earthquakes, volcanic eruptions, and tsunamis can cause significant damage to communities, infrastructure, and the environment. Understanding plate tectonics helps us prepare for these events, minimize risks, and protect lives and property. The study of geological processes also aids in resource discovery and environmental management, making it essential for sustainable development. Geological processes are natural forces that shape Earth's physical makeup. These processes include folding, faulting, volcanism, and earthquakes. Geologists study these phenomena to understand the planet's history, locate resources, and predict disasters. Geological processes constantly change the surface of the Earth, creating mountains, valleys, and other landforms. They are divided into two main categories: endogenic internal and exogenic external forces. Endogenic forces originate from within the Earth and create irregularities on the surface. These internal forces break, bend, and fold rock layers, forming ups and downs on the crust. Major endogenic processes include folding and faulting, which lead to the creation of mountains, valleys, and other landforms. Understanding endogenic forces is crucial for explaining the dynamic nature of Earth's surface. Folding occurs when rock layers are pushed sideways by Earth movements. Compression from one or two directions causes the layers to bend, forming upfolds, anticlines, and downfolds, synclines. Continued compression can create asymmetrical folds, overfolds, and overthrust folds. These structures are fundamental to the formation of fold mountains and are key features in geological landscapes. Old mountains are classified in two categories: young and old. Mountain building periods known as orogenesis have occurred over the last 400 million years. Old fold mountains formed during earlier periods, while young fold mountains such as the Andes, Rockies, Alps, Himalayas, Atlas, and Australian Alps were created during the Alpine orogeny. These mountains are prominent features of Earth's landscape and provide valuable insights into geological history. Faulting is the process of cracking the Earth's crust due to tension and compression. Faults can occur along single lines, displacing rocks upward or downward. Parallel faults may cause land between them to sink. Rift valleys or rise block mountains. Rift valleys like the East African Rift Valley and block mountains such as the Afar Horst are direct results of faulting. These landforms are significant in understanding Earth's structural changes. Earthquakes are sudden ground movements caused by shifts in rock masses below Earth's surface. The release of energy sends shock waves through the rock, shaking the ground. The focus is the point of origin while the epicenter is directly above it. Earthquakes are measured by seismometers and recorded on seismographs with magnitude given by the Richter scale. Most destructive earthquakes are linked to crustal ruptures and faults, causing dramatic changes and damage to structure. Earthquakes generate seismic waves that travel through the Earth. There are two main types: body waves and surface waves. Body waves include P primary and S secondary waves, which travel within the Earth's body. Surface waves, named Love and Rayleigh, move along the surface and are responsible for much of the damage during earthquakes. Seismographs can detect these waves even on the other side of the planet, helping scientists locate and measure earthquakes. Most earthquakes occur along two major belts: the Circum-Pacific Belt, Ring of Fire, and the Mediterranean Asian Belt. The Ring of Fire encircles the Pacific Ocean, accounting for 80% of earthquake energy. The Mediterranean Asian Belt passes through Europe, North Africa, and Asia, contributing 15% of global earthquake energy. Other seismic belts are found along mid-oceanic ridges and the Great Rift Valley of East Africa. These belts coincide with mountain ranges and volcanic activity. Volcanism is the process by which molten rock, magma, gases, and solids are expelled onto Earth's surface. These can occur slowly or violently, creating various landforms. Magma reaches the surface through vents, pipe-like openings, or fissures, large cracks. Lava emerging from vents builds volcanoes, while lava from fissures spreads out, forming plateaus. Volcanic activity alternates between active and dormant periods, shaping landscapes and influencing climate. Volcanoes are classified by shape and size, determined by the type of volcanic material and eruption style. Shield volcanoes have broad, low profiles formed by fluid lava flows like those in Hawaii. Stratovolcanoes are steep cones with alternating layers of lava and rock fragments, characterized by explosive eruptions. Cinder cone volcanoes are conical hills of cinder-sized debris. Calderas are large basin-shaped depressions formed when a magma chamber drains and the cone collapses inward. Volcanoes are also classified by activity: extinct, dormant, or active. Extinct volcanoes are unlikely to erupt again, like Mount Zukwala in Ethiopia. Dormant volcanoes are currently inactive but may erupt in the future, such as Mount Kilimanjaro in Tanzania. Active volcanoes have erupted in the last 500 years, like Erta Ale in Ethiopia. Understanding volcano types and activity levels is vital for hazard assessment and land use planning. Magma cools and solidifies within the crust. It forms intrusive or plutonic igneous rocks. Batholiths are large dome-shaped intrusions located deep in the crust, sometimes forming mountain cores. Sills are horizontal intrusions between rock layers, creating parallel sheets. Dikes are vertical intrusions formed as magma rises through cracks, creating wall-like structures. These landforms reveal the hidden processes shaping Earth's interior. Style of volcanic eruptions and types of lava are closely linked to plate boundaries. Basaltic lava is common at oceanic divergence zones and mid-oceanic volcanoes, where ocean plates collide. Basalt and andesite dominate. Near zones where ocean and continental plates converge, consolidated ash flows are found. Understanding these relationships helps geologists predict volcanic activity and assess risks. Exogenic forces act on Earth's surface from the outside, including running water, wind, moving ice, and sea waves. These forces level the ups and downs of the land through denudation and deposition. Denudation involves weathering and erosion, breaking down rocks and transporting materials. Exogenic processes are essential for shaping landscapes and creating new landforms. Physical weathering breaks rocks into smaller pieces without changing their chemical composition. Key processes include thermal expansion and contraction, frost action, and plant and animal activity. In hot, dry areas, temperature changes cause rocks to expand and contract, leading to exfoliation. Frost action occurs when water freezes and cracks, expanding and breaking the rock. Plant roots and animals also contribute by widening cracks and breaking rocks apart. Chemical weathering changes the internal structure of rocks, often through rain action and the activity of plants and animals. Rainwater containing dissolved oxygen and carbon dioxide reacts with minerals like carbonates, especially in limestone. This process creates caves and underground rivers. Bacteria and decaying vegetation produce acids that further break down minerals, weakening rocks and contributing to landscape evolution. Erosion is the movement of soil and rock particles by agents like running water, wind, sea waves, and glaciers. Deposition occurs when these materials settle and accumulate, forming new landforms. Running water is the most powerful agent, shaping valleys, gorges, and floodplains. Wind creates features like sand dunes and less deposits, while sea waves form beaches, spits, and lagoons. Glaciers carve out unique landscapes, contributing to Earth's diversity. Water erosion creates various landforms along river courses. In the upper course, rivers cut deep gorges and V-shaped valleys. The middle course features wider valleys, meanders, and oxbow lakes. In the lower course, rivers form floodplains and deltas, depositing sediments and creating fertile land. These processes are vital for agriculture and ecosystem development, shaping the landscapes we depend on. Wind is a powerful force in desert and semi-desert regions, creating unique landforms. Sand dunes are hills formed by sand accumulation around obstacles. Barcons are crescent-shaped dunes, while less deposits are fertile soils transported by wind. These features are prominent in areas like North China and contribute to the diversity of Earth's landscapes. Sea shapes coastlines through erosion and deposition. Beaches are strips of land covered by sediments, while spits are narrow deposits extending into the sea. Lagoons are areas of salt water separated from the sea by sandbanks. These features are important for coastal ecosystems and human activities, illustrating the power of external forces in landscape formation. Mass wasting refers to the downslope movement of rock, soil, and regolith under the influence of gravity. Factors like water, slope angle, and human activities contribute to mass wasting. Water reduces cohesion among particles, increasing movement. Steep slopes are more prone to mass wasting, and human activities like farming and overgrazing can trigger events. Mass wasting can cause destruction of property and loss of life, highlighting the importance of understanding these processes. Human activities can influence geological processes, especially mass wasting. Farming, construction, and overgrazing on steep slopes create conditions for landslides and soil erosion. Understanding how our actions affect Earth's surface is essential for sustainable land management and disaster prevention. By respecting natural processes, we can reduce risks and protect our environment. Advances in geology and technology allow scientists to predict geological events like earthquakes and volcanic eruptions. Seismographs, satellite imagery, and computer models help monitor plate movements and assess risks. Early warning systems save lives and reduce damage, emphasizing the importance of geological knowledge in modern society. Continuous research and education are key to improving prediction and preparedness. Geological processes help locate valuable resources such as metal ores, oil, and minerals. By studying plate tectonics, folding, and faulting, geologists identify areas rich in resources. This knowledge supports economic development and sustainable resource management. Understanding geological history is essential for efficient exploration and extraction, benefiting society and industry. Plate tectonics influences the composition of the atmosphere and oceans, serving as a prime cause of long-term climate change. The movement of plates affects volcanic activity, mountain formation, and ocean circulation, all of which impact global climate. Understanding these connections helps scientists predict future climate trends and develop strategies for adaptation and mitigation. Study of geological processes reveals the evolution of Earth's surface over millions of years. Continents drift, mountains rise and fall, and oceans expand and contract. These changes are driven by plate tectonics, endogenic and exogenic forces, and human activities. Understanding Earth's evolution helps us appreciate the complexity of our planet and the importance of preserving its natural system. Ethiopia's geological history is marked by the formation of continents, rift valleys, and volcanic activity. The East African Rift Valley is a prominent feature, created by divergent plate movements. Volcanic eruptions and earthquakes have shaped the landscape, influencing human settlement and development. Studying Ethiopia's geology provides valuable insights into regional and global geological processes. Throughout this unit, we've explored the theory of continental drift, plate tectonics, and the major geological processes shaping Earth. We've learned about the movement of plates, types of boundaries, and the forces driving these changes. The impact of geological processes on human lives, resource discovery, and climate change highlights their importance. By understanding these concepts, we can better predict, prepare for, and adapt to Earth's dynamic nature. As we conclude our journey through major geological processes, remember that Earth's surface is constantly changing. The study of plate tectonics and geological forces is essential for understanding our planet, predicting natural events, and managing resources. Continued research and education will help us adapt to these changes and protect our environment. Stay curious and keep exploring the wonders of Earth's geology.